Okay, so I'll talk to Fields about getting the when the videos and slides will appear. Okay, and I'll think a bit about the logistics for the trying to get things ready in advance. I mean, I have things in advance. I mean, obviously what I'm showing you is already here, but I'm not quite sure how far I'll get today, but I better get started. Is there no questions? So I was talking about viewing eigenvectors as functions, and I know from past experience that this is always confusing and somewhat difficult to get your head around. So I worked some examples, and I want to continue to work a few more. So the first couple of examples looked at were regular graphs, and just for variety, I wanted to look at well, and for other reasons too, I want to look at the paths on n vertices. Let's say we start at 0. So the point here is that P sub n is the path on n vertices. N is the number of vertices, not the diameter. Okay. Now, so the exercise is to get the or at least get information about the eigenvalues and eigenvectors. Now, I probably should do this in a different color. So the first thing I want to think about. Well, okay, so we're going to have an eigenvector. Now, if we have an eigenvector, any non-zero scalar times that is again an eigenvector. So if we look at the entry of the eigenvector on the function on the first vertex, we can assume it's 1 or it's 0. They're the only two possibilities. Okay. Now I want to think about the case where it's 0. Actually, I'll do this in red because it's going to get crossed out. So if this is 0, now let's suppose that our eigenvalue, I'm going to use theta. Okay, so we're going to construct an eigenvector, and we have the balance condition that eigenvalue times the value of the function, the vertex, is equal to the sum of the weights of the neighbors. So theta times 0 is 0. So the sum of the weights of the neighbors of this vertex must be 0. That means this must be 0. And so it's turtles all the way down. So there's no eigenvector for Pn that is 0 on the first coordinate. Actually, that's probably worth writing down here. What am I doing? Colors, right? So 1, no eigenvector. So we can assume that we're 1 on the first vertex. So assume the okay, so I can erase that. And what color? Okay, so now we run through the same calculation before. We have that theta times 1 is the sum of the weights of the neighbors, but there's only one neighbor. Okay, and so its weight must be theta. Okay, so we've got the second entry. Okay, well, that's good. So let's repeat the process. The next step is we're going to have theta times theta is equal to the sum of the weights of the neighbors. And so the next entry must be theta squared minus 1. And I'll go one step further just to put a 3 here. So then I would get use all these columns. Theta times theta squared minus 1 equals theta plus. So this is theta cubed minus 2 theta. And actually, I do want to go make an extreme out of this. there. So this is just to make things big enough to be interesting. So then I get that theta times theta cubed minus 2 theta is equal to theta squared minus 1. And so this becomes theta to the fourth minus 3 theta squared plus 1. Now, the point is that I can continue this until I run out of vertices. Okay, and so let's think about what happens. And so I'll claim, well, this is letting you an exercise, we get a recurrence for the kth entry. Now, so you're getting a sequence of polynomials. In fact, these are versions of the so-called Chebyshev polynomials, which is not important, but I'm just trying to put for us at this point, but they're not just some random sequence of polynomials. But let's think about, okay, this path is finite. So let's think about, suppose that the path was on 5 vertices. Okay, we've done all these calculations. Now, the issue is that what happens to let's pretend we're trying to compute the weight on the next vertex. Well, there can't be weight on the next vertex because there's no vertex there. And so what we're going to have is that, I can do it here. We're going to have that theta times theta to the fourth minus 3 theta squared plus 1 is equal to theta cubed minus 2 theta squared. And that gives us that right here, theta to the fifth. That's theta to the fourth there. Actually, I don't like that theta to the fourth there much. So theta times this is equal, no, that's just theta squared, theta cubed minus 2 theta. Okay, so, and that's about here in theta. So we have theta to the fifth minus 4 theta cubed plus 3 theta. Now, that's going to be the weight on the 6th vertex, which is not there, so that has to be 0. So by looking at what happens at the right-hand end, so from looking at the last, we get a polynomial which must have, which has theta as a 0. So not only have we found the eigenvector, but we've also determined that the theta is a 0 of this polynomial. Now, there are 5 choices, and so your first question might be, which of those choices is right? Well, the answer is they're all right. Any theta which satisfies this will give you an eigenvector with eigenvalue theta. And you've got 5 choices. Theta equals 0 is 1. Notice if theta equals 0, the vector is 1, 0, minus 1, 0, plus 1, minus 1. So the vector is well defined. It doesn't turn into a 0 vector. Okay. So the point is, by doing this calculation, we get, in fact, a formula for the characteristic polynomial of the matrix and an explicit eigenvector. And the other thing to bear in mind is that if you're dealing with a symmetric matrix, then eigenvectors belonging to distinct eigenvalues are orthogonal. So if I choose a different value of theta, let's call it tau, and I do the computation, and I get a second eigenvector, those 2 eigenvectors are orthogonal, which is telling you something unusual about the polynomials. Now, I'm not going to go into that. It's not relevant for what we're doing. But my point is, simply by thinking of the eigenvector as a function and applying our basic recurrence, we can get quite complete information about the eigenvalues and eigenvectors for the path and n vertices. Now, the issue here is it shouldn't be clear to you that this polynomial the zeros of this polynomial are distinct. They are, and it's not too hard to prove, but I'm not doing it. You can probably do it from what we've got here, but I'll leave it at that. So that's the path and n vertices. Any questions at this point? Okay. The other graph I thought I'd look at in a bit more detail is the Peterson graph. Now, for Peterson graph, I am not going to find all. Well, actually, I am going to find all the eigenvalues, but it's not going to be. The fact I have all of them won't be proved. Okay, so I want to construct an eigenvector. Now, the Peterson graph is regular, so the constant functions, non-zero constant functions, are eigenvectors, and so the all ones vector is an eigenvector, and the other eigenvectors are orthogonal to that. Okay, so I mean, now this is an instance of the situation I was saying before, that the best way to get the eigenvectors and eigenvalues of the matrix is to guess the eigenvector and then read off the eigenvalue. So I need a vector which is orthogonal to all ones vector. Well, this certainly works. I've got ones on the outside 5 cycle and minus ones on the inside 5 cycle. So the entries that vector sum to 1. So that's a function which, sorry, sums to 0. So that satisfies at least the condition that the entries are orthogonal to 0. Sorry, that the entries are orthogonal to the all ones vector. Now, so is it an eigenvalue? Well, now we've got to go in and do our check. Now, so let's pick a vertex, pick this guy. The sum of the weights of his neighbors is 1. Now, if you pick this guy, the sum of weights of his neighbors, actually, look at that, right? It's got weights his neighbors. It's got 2 minus 1s and a 1, so it's sum of the weights of his neighbors is minus 1. Yeah. Now, you can more or less see by symmetry that this is going to work all the way around. And so what we get is we get an eigenvalue one. Okay. So and the corresponding eigenvector is 1 on the outside cycle and 1 on the inside 5 cycle. Now, in fact, Peterson's graph's there's lots of 5 cycles of Peterson graph, and each time you find one 5 cycle, you delete those 5 vertices, and that takes away 10 edges. There are 5 edges left over, so what's left over is a 5 cycle. So in fact, there are 6 pairs of 5 cycles, and for each of these you get a vector. And clearly that they're not all going to give you. Some of them, it could be possible that one of them is a scalar times the other, but it's clear that some of them aren't. So you're going to get more than one eigenvector. In fact, you get the full set, but it's not obvious from what we've seen, so we won't go any further than that. We have one eigenvalue. So I should also say we have an eigenvalue 3 coming from the all ones vector. Now, can we get some more? Now, the one reason I wanted to talk about the Peterson graph is because the eigenvalue bound for Coke-Leaks is tight for the Peterson graph, and I wanted to go close to demonstrating that. So I have to pick a vector which is orthogonal to the constant vector and also orthogonal to the vector I just constructed. Okay. Now, I'm not going to worry too much about that. If I construct a second eigenvector which with a distinct eigenvalue is not 3 and not 1, it must be orthogonal to the constant vector and to the eigenvalues of 3 equals 1, because eigenvalues of a symmetric matrix with eigenvectors of a symmetric matrix with distinct eigenvalues are orthogonal. So I don't have to do any work to the orthogonality. I just have to make sure that it's there. And that its eigenvalue is different. And again, we do the same calculations before. So we look at the 3. Now it's got, is it doing this right? Yes, okay. It's got, yeah, so it's got 3 neighbors, each weight -2. So I get give me -6, so that would be a -2, assuming everything's going to behave itself. And if we check on this, the sum of the weights of these guys, it's got a 3, and a -2, so that's 4, and that's going to give me a -2 as well. So we get an eigenvalue -2. Now, how did I choose the weights? Well, how did I divide things up? Well, let's clear this up a little bit. So let's look at the 3s. That's not what I meant to do. Okay. Sorry. There we are. And I wanted red. So there are 4 vertices with 3s. 6 with -2s. So 4 times 3 is 12. -12 is 0. So it's orthogonal to the all-ones vector. But the point, as I claimed, is that these 4 vertices form a co-colligator size 4. Obviously, they're not adjacent. I'll make that a bit more obvious in the next slide. But so they form a co-colligator size 4. Okay, and so you've got a co-colligator size 4 in the Pearson graph. You've got 4 vertices, no 2 adjacent. They've each got 3 neighbors coming out. So there's 6 vertices over here. Now, 4 times 3 is 12, so the most regular situation would be for each of these guys to have 2 neighbors over here. And in fact, if you check, they do. So this is what's helping you. But the point is that I constructed my function by choosing one weight on the vertices, the co-colligator, and one weight on the rest. Now, in general, this doesn't work. But if your graph has got, if the partition that you're using is nice, then it does work. The definition of nice is equitable. We won't be going about that for quite a while. So we've got the eigenvalues 3, 1, and -2. Now, 3 is definitely the largest. And as it turns out, -2 is the smallest. And so the eigenvalue bound is alpha bounded by v in 1 minus k on tau, which is 10 in 1 minus 3 on -2. And that's equal to 4. So if this is the least eigenvalue, then the eigenvalue bound is 4. And that's exactly what we see. There's a co-colligator of size 4. Now, it's not easy in general if I give you an eigenvector and say, does this have the smallest possible eigenvalue? That's in general not an easy question, and though it does matter sometimes. Now, I wanted to make it a bit clearer about where that co-colligator is coming from. So, I mean, the standard definition of the Pearson graph is to draw the graph on the board the way I just did. The most useful definition is to say the Pearson graph consists of 10 unordered pairs from the set 0, 1, 2, 3, 4, with 2 pairs being adjacent, two pairs being adjacent as vertices if they're disjoint. And so the trick with the Pearson graph is to take the first pair to be, the obvious thing to do is take the first pair to be 0, 1. And that gets you in a mess. Take the first pair to be 0, 2. Now, the Pearson graph's got this rotational symmetry. So if I add 1 to 0, 1 to 2, I get 1, 3, 2, 4, 0, 3, 1, 4, and 0, 2. And so I get 5 pairs, and each of them is adjacent to the one before it and one after it. So you can view this as a happy accident. And then, okay, so 0, 2 has got to be adjacent to 3 pairs. And we've already used up 1, 3, and 1, 4. So anything left over is 3, 4. And so once you choose 0, 2 and assume that you're invariant under this rotation by 2 pi and 5, then you get this labeling. So the Pearson graph consists, as I said, of the 10 unordered pairs from a 5-element set. Now, there are 4 pairs that contain a particular element of this set. So I've labeled or indicated the 4 pairs that contain 1. Now, no 2 of those are adjacent because any 2 of them have 1 in common. And so they form a cocleek. And so we can then see that, in fact, there must be at least 5 cocleeks, the ones that contain 1, 2, 3, 4, and 0. Okay. And so if you're trying to prove things about the ordinals and do with the Pearson graph, which you might have to do in the exercises, then this is the picture you want to start with. Any questions at this point? So I'm going to change topics completely now, and I want to talk about some products. Now, for the moment, I'm going to give some constructions and use it to construct some graphs. But the products I'm talking about are important in terms of the physics as well. And so I'll say a little bit about that today, but not too much. Now, I'll be talking about tensor and Kronecker products. And for as far as we're concerned, you can regard the 2 terms as being equal. I use them slightly differently, but I'm not expecting you to worry about it. So there's some complications. The first thing is you don't want to look up the physicist's definition of a tensor, because it won't help you if you're a mathematician. I'll say a bit more about that as I go on. So when a physicist talks about a tensor, they normally mean what I would call a tensor field on a manifold, and that's because that's what they're dealing with. But we're just talking about well, to understand the tensor field, you understand tensors in a certain sense. So I'm going to define the Kronecker product is just an operation on sort of on explicit vectors, and so it's as concrete as you want, but it doesn't. The vector products have lots of interesting properties, and you don't see them if you get down too much in the details. So I'm going to start by defining the tensor product of 2 vector spaces. Now, if I was trying to give a detailed treatment of tensors in a math course, then I would probably have to start with tensor products of modules. Okay, but we're not doing that. We're just going to do vector spaces. Now, so we're going to have 2 vector spaces, V and W. And for our purposes, everything's finite dimensional. I'll give you a lot of warning if something is not. So we're just assuming they're finite dimensional. And so we're going to construct a new vector space, V tensor W. So I always, when I'm taking products of spaces, I'll be using the term tensor product. When I come to taking products of vectors and matrices, I refer to that as a Kronecker product. But as I said, you're not required to worry about that. So what I'm giving here is not really a definition, but I think it might be more useful. So we're going to construct a vector space V tensor W. Now, intuitively, if that's the right word in this context, the idea is to think of V, actually think in terms of dual spaces. So you have linear functions on V and linear functions on W. And the dual space here is the bilinear functions on V tensor W. So a bilinear function takes a vector of V and a vector of W and returns a scalar. And there's linear in each coordinate. Okay. And so in a sense, the purpose of tensor products is to deal with bilinear products in place of, and bilinear maps in place of linear maps. So you're in a situation, you want to deal with bilinear maps. In a sense, there's 2 options. One is to work out the theory of bilinear maps, where we work out the theory of linear maps. But what we actually do in practice is replace our vector spaces by something a bit more complicated. And so then our bilinear maps will turn into linear maps in the new situation. So the idea is you have to choose between complicating the object and complicating the maps. It's best to complicate the object. And so in this case, we're complicating our objects. We're constructing this tensor product of vector spaces. So you can view this new vector space as a set of symbols like this, where V is in first vector space and W is in the second. So, and we have some rules. And the first 2 rules are just saying that you're distributive, additive in each term. And the third is the scalar operation. Okay. Now notice that alpha V tensor alpha W will be alpha squared V tensor W. So there's some nonlinearity hiding there. But my point is, we have these things, and we operate them on the most natural way. Now, there's a sense in which, if you're doing simple calculations like this, there's nothing too difficult about dealing with tensors. But never think that tensors are simple. And what happens is the situation always keeps on getting more complicated. And every time it gets more complicated, you realize the tensors don't work exactly the way you thought. So don't be surprised if the first when you start looking at this, that it's not easy to see what's going on. And you will work out some framework that makes sense to you. And then a few weeks later, you'll discover it's not quite right. And all I can say is this is the normal procedure. We all have to go through this. But so we've got this vector space. So we just operate on these symbols. Now, so if you choose, well, I said if I take all vectors of form little v tends to little w, there's going to be far too many of them there to form a basis. And so it is true that if E1 through EM is a basis for V and F1 through En a basis for W, then these products are going to be a basis for the product. So the dimension of the tensor product is the dimension V times W is the dimension of V times the dimension of W. Okay. Now, and so we would call this thing, which I've sort of half constructed, the tensor product. Now, what I've done there is given you sort of an abbreviated version of the abstract definition of a tensor product. Now I'm going to go to something which I think you'll find simpler, and that's to write it out in terms of explicitly in terms of entries. So, okay, so it's best to start. When we're dealing with tensor products, we'll normally just be taking products of vectors and products of matrices. We won't need to go any further than that. You can do worse, but we're not. Okay, so we're going to define the tensor product of a K by L matrix with an M by N matrix. Now, it's worth realizing here that one of K and L could be 1, and one of M and N could be 1. So these matrices could be what you would call vectors. Now, I always feel a bit uneasy at this point because matrices form a vector space, and so if you take an element of a vector space, surely it's a vector. But anyway, so this matrix, your point of view, could well just be a vector. Okay, I'll come back to that in a bit. And so the Kronecker product, okay, now this is just a straightforward operation. You replace the ij entry of A by the ij entry of A times the matrix B. Okay, and so you take two modest size matrices and you get a big matrix. Now, this works for vectors. Actually, I'll put it in here. No, it's not one. We do this in a couple of ways. So we're going to replace the first entry of this by 1 times 3, 4, so you get 3, 4, and the second entry by 6 and 8. The reason I wanted to do this was because of this. 3, 4, and then 6, 8. So now this is of course the outer product, or what is often called the outer product. Of the two vectors. Okay, so yeah, so that so that it's tempting to say that the tensor product of two vectors, two column vectors, is a column vector. I feel slightly uneasy about that because if you look up the actions vector spaces, there's nothing in there about row vectors and column vectors. But anyway, we can. There's a fair bit of confusion that goes on. So the now in general, of course, we've got matrices and things get too big too soon. I mean, if I take so I'm not going to try and write them down. It might be worth just digressing a little bit. If A is M by N, then vec A is the matrix, sorry, is the vector AE1 tangent. So these are the columns of A. Now, this is a very useful operation. So vec maps, well, M by N matrices to Mn by 1 matrices. It's a linear map, actually. And if you make the right choices, it also preserves the lengths. So it's actually very useful when you're dealing with chronicle products. Okay, so the other comment I want to make is you can, if you're dealing with the chronicle product 2 matrices, and you want to know what the entries are, well, you can write down, the formula is written down here, that the problem is that you don't really want to think of the rows and columns as being indexed by integers. You want to think of the rows and columns as being indexed by ordered pairs of integers. Okay. And so and if you do that, then well, you get this equation here. Okay. Now, in my experience, it's best to try and avoid thinking about the actual entries of a tensor product, but you can do it. It's just that you have to assume that the rows are labeled by ordered pairs and the columns are labeled by ordered pairs. Okay, and then you can so you're basically taking picking out a column. You go along here, you find the ith block, and then you pick the jth column in that block, and so that the ordered pair corresponding to that is I, j. Okay. Any questions at this point? Okay. Now, there's another way of defining the product of 2 operators, which doesn't require us to, which means we just have to, well, I'll do it and see why it's good. So you can define the product of A times B to be the thing which takes U tensor V to AU tensor BV. Now, there's an issue with this definition in that if you want to define a linear map, you can define it by specifying its values on a basis. If you try and specify its values on a spanning set, then you've got to do some checking to make sure everything's consistent. Now here I'm defining it by an operation initially on a spanning set. And one of the nice properties of tensors is that still works. So I could also simplify things by just assuming that U was running over a basis, B was running over a basis, and then extend by linearity. But to some extent, you can treat the set of pairs V comma W as though they're a basis, but they're not. In general, there's too many of them. But the point about this is now you've defined it, a product of these 2 things. Okay, and so this gives you another way of defining the tensor product of 2 operators in terms of the tensor product of vectors. Okay. And so we'll leave it at that. Now, so as I said, since I won't be taking, I mean, I could take a vector V tensor product of matrix A, and then try and take it, and then take a tensor product that with a second matrix B. Okay, that's all well defined, but in practice we won't really get that far. So we'll be dealing with products of tensor products of 2 vectors on matrices. And as I've indicated earlier, if I view vectors as n by 1 or 1 by n matrices, then I can just deal with, and you need to define the tensor product of matrices or the chronic product of matrices. Now again, we get the obvious properties. So that the tensor product is distributive in each term, and you get the same rule for scalars. Okay. An important property this is worth giving it, is that assuming that the required products exist, that the product of A times B with C times D is AC times BD. Since I'm listing the properties, the other property which is useful is that the trace of A times B is just trace of A times trace of B. This is dead easy. You can see there's lots of ways. So none of these are difficult. One comment about this, sorry. One comment about this is if I think of A and B to be, or let's say N by N matrices to make it life easier, and C and D to be N by N vectors, or take C to be an eigenvector for A and D to be an eigenvector for B, then you get that, well, in this case, if you take A times B, apply it to Y times Z, then you get that Y times Z is an eigenvector with eigenvalue lambda mu. So this tells you that the product of the eigenvalues of the factors gives you eigenvalues of the product. Okay. Now the challenge is to prove the other direction. So it is in fact true that every eigenvalue of the Kronecker product is a product of eigenvalues of the factors, but this argument doesn't give you that. This is probably going to end up in your lap as an exercise. And there's a third product which is going to be quite important for us, and this is called the Scher product of two matrices A circle B. This is much easier. The IJ entry of the Scher product of A and B is just the product of the IJ entry of A with the IJ entry of B. So it's sometimes called the, I can't resist this, bad students product. Now it turns out it is useful, and we'll see it coming up before too long. Okay, so of course it's dead simple. It's distributive in each factor. It's commutative. A circle B is equal to B circle A. Okay, so it's the comment I want to make is that A circle B is a principal submatrix of A Kronecker B. And you may want to think about that. The easiest way to do these things is to just write out for a 2x2 case, and you'll convince yourself very quickly. And then no one's going to ask you to write out a proof in the more general case. It also interacts nicely with the Kronecker product, and we've got this identity here that the Scher product of A Kronecker B with C Kronecker D is the Scher product. Okay, so now the Scher product is sometimes referred to as a Hadamard product, but I talked to Snyder, is sort of one of the real experts in linear algebra, and asked him about this once, and he says, well, Hadamard never used this product, but Scher did, and Scher also proved a non-trivial theorems about it. So I will call it the Scher product. I generally call it the Scher product, but you will see people call it the Hadamard product. Now, one place we'll be using the Scher product is we can find a different expression for the matrix, what we're calling the matrix inner product. So this is the trace of A star times B. It can also be written as you take the Scher product of the complex conjugate of A with B, and then you take the sum of the entries of that matrix. So I'm using so sum M is defined to be sum of Mij over Ij. Now this is a perfectly natural operation on matrices. It's linear. Okay. And it's sometimes useful, it's sometimes more convenient to compute the Scher product or to compute the inner product using this formula than it is using that formula. It does not going to matter in the short term. I might find an exercise to give you some practice with it. But so we have this second product. We can use it to get a second expression for our inner product, and that's quite important because this inner product plays a big role. And so if you've got different ways of looking at it, that can have an impact. Now we're going for time. The theorem that Scher proved that I just referred to is that if A and B are n by n matrices and they're positive semi-definite, then so is their Scher product. Okay. Now, I think there are 3 or 4 different proofs of this. And at the moment, my inclination is to put this on the list of exercises. There are some quite short proofs. Well, to give a broad hint, first think about the rank 1 case. If you verified this for rank 1 matrices, and then try and use the theorem to prove it for the general case, I think that might be the simplest proof. But so, as I said, there are a number of ways of proving it. You can deduce it. Well, where was it? You can deduce it from this fact. Because, that's if you prove that the Kronecker product of 2 matrices that are positive semi-definite is positive semi-definite, okay, and then principal submatrices of positive matrices are positive semi-definite. Okay. Now you've got to be a little careful. How do I prove that this is positive semi-definite? I'd like to say, well, the eigenvalue is non-negative, but we haven't proved that because we haven't determined the eigenvalues of the tensor product yet. It is in fact true that but on the other hand, it is in fact true that the eigenvalues of A times B, that the eigenvalues of A times the eigenvalues of B, and you may use that. I may eventually ask you to prove it, but you may use that in any other exercise. Okay. I don't want to make your lives more miserable than they have to be. So we have Scher's theorem. Okay. Now, I said tensors are a lot intense. So as I said, just explain my usage. I think of the Kronecker product as when I write down, A sub ij times B. I'm writing down the Kronecker product, so I'm using explicit formulas for entries that I view as the Kronecker product. When I take the product of 2 vector spaces, that's an abstract operation, and I don't have to write those vectors down in any particular form. Okay, and then so I'm taking the tensor product of vector spaces, and the general operation is take tensor products of modules. That is a lot more complicated than dealing with tensor products of vector spaces. Okay, and basically each time you try and generalize things a bit, the tensor product will carry through, but everything gets 1 step stranger. Now I wanted to talk a bit about tensor products of algebras. I think if A and B are algebras, so that we just think of these algebras for our purposes as matrix algebras. So the vector spaces are matrices closed under, closed on multiplication. And in that case, if A and B are algebras, then the set of matrices, A Kronecker B or A Kronecker B, whatever, spans an algebra, which we denote obfuscation by A tensor B. Now, this is following from this A tensor B, C tensor D identity I wrote down earlier. Okay, so we get an algebra. Okay, now sitting inside that algebra, we have actually this. Now I claim that this is a subalgebra. Now the problem is it's clearly closed under multiplication because I times I is the identity, but when I add them, it's not quite clear what's happening. And so, but the issue is that if you find yourself with a non-zero scalar in front of the I, you just push it across to the left in front of the A. So this is indeed a subalgebra, for what that's worth. Now, the algebras we're going to use, I said, will be algebras of matrices, and in the extreme case, you take the full algebras of matrices. And so here I'm taking the obvious, n by n matrices, n by n matrices, and the third space W, which is going to consist of m by n matrices. Now, in this up, if m's in W, we have a map which sends m to A, M, B star with A and curly A and B and curly B. Now that's a linear map. Okay. And I don't believe it's, actually it's not true, but it's a homomorphism. Well, okay, yeah, I'll be careful. Yeah, okay, no, sorry. This map from M to A, M, B star is just a linear map. But the issue is I've got two operations now. I've got the vectors, I've got the products, the elements of this algebra, and I have these maps on W. So the map I've written down here is an endomorphism of W. It maps W to itself. Now the linear maps take W to itself, form an algebra. I haven't given it a name because I'm going to have m times n times m times n. It's a mess. But so the linear maps from W to itself form an algebra. And curly A tends to curly B is an algebra. And my claim is that this map is an isomorphism between those two algebras. And so in fact, what you get this statement. Oops. That the algebra A tends to B is isomorphic to the endomorphisms of this. Now, this is a very important property of the tensor product and turns up at various points. It actually holds a bit more generality than what I've written down. But and maybe I should talk about this more later on, but I'm running out of time. But the statement it simply is that this algebra is isomorphic to this algebra. Okay, and this turns out to be useful, and I'll leave it at that. And I'll just remark that the general form of an element of the endomorphisms of M by N takes a matrix M and maps it to this product of this form. The stars in here to make the map a homomorphism. Otherwise, you get some order reversing when you don't want it. Okay, so we will probably need to use this at some point. Okay, which is so it's not sort of, you don't normally haven't had occasion, I guess, to think about the endomorphisms of the ring of M by N matrices, but we will need to, and it's actually related to the tensor product. And this is one of the reasons why the tensor product is important, because it gives you a way of dealing with these somewhat nastier things in terms of tensor products. And okay, so this is why I was saying, well, I knew I wasn't going to do all this, but this is why I suppose I can post in advance. So I'm going to stop at this point. What I'm going to do next is show how we can construct some interesting graphs using the tensor product. Tensor products also play a very important role in quantum mechanics, and I'll say a bit about that too. But basically, I haven't really gone into details about it. I've given you a bare minimum in a certain sense, but if you have a pair of quantum systems, then you're going to be working with a tensor product of vector spaces, and tensor products of algebras. And a lot of the strangeness of quantum mechanics is coming from that fact. Okay, so there's two sources of strangeness. There's the fact that you've got this randomness, and the third is and the second is that you have these tensor products occurring, and that makes that those two things account for the strangeness of quantum mechanics. And I think it's very fair to say that the tensor product is causing you the most problems. Now, it won't matter too much for what we're doing, so I won't need to go into that, but I will discuss it. But that's it for today.